Now we start to study Fourier series. First encounter with Fourier series. Testing. Let's make some tests. Okay, and now let's define our function. And so let's just do it in a simple way. X is X takes values from 0 to 2 pi, and we need maybe quite many points. Let's put here, for example, something like 2000 points. Here are our X evaluation points from 0 to 2 pi, and now we define our function, and let's first take something something like let's put f to grow linearly from 0 to pi in the interval from 0 to pi. So now after this command, of course, f is just the identity function equals to x. But let's put here f for the values where x is larger than pi. Let's put this to be 2 times pi minus x. I'm not sure if you follow my thinking here, so let me show it as a picture. Let's make a plot window, and let's plot like this. And actually, as usual, let's have here we need to do the line width, and actually we need to do the font size anyway at some point. So let's do it. Let's plot this with red line and using the line width we chose up there. Okay, so this is quite a short. And already there's an error. Man, what's the error? Oh, of course, sorry. Minus x. Let me put it this way actually. So let's choose an index. So this index is same size of vector x and contains ones in the place where this logical statement is true. So we have here, we are only changing the f vector in the points specified by this index, and of course we need also here to use the same index. Hey, for whom this is completely clear, what is this index thing? No one. Okay, thank you. I'll show you. So this is just a test vector from 1 to 5, and let me make an index using a logical. So temp is bigger than 3, for example. So now you see this is a logical array. It contains zeros for the points where the temp elements are not larger than 3, and then it contains ones for these two guys that are larger than 3. Okay, who thinks the index thing is clear now? Excelente. So what I'm doing here is, first I take the function f to be just x, the identity function at all points of x, but then I change the definition, but only at the points where x is bigger than pi. So what I'm doing actually is, so first I take f to be this one, but then from now on I'll put it to be this one. So then I'm constructing this function. Okay, let's plot. And here we see just now the first function we are trying to represent as Fourier series. Okay, and then let's do zeroth order Fourier approximation. So we only use the constant, namely f of x equals a0 with a0 computed as integral of f let's check what was the definition of a0 here. It's the average of the function f. So we integrate f over the domain from 0 to 2 pi, and we divide it by the length of the integration interval. Okay, so all right, so now we need to I will do this in an extremely simple way now. A0 equals 1 over 2 pi times, and now I'm using just the midpoint rule, the most simple of numerical integrations maybe. So I take the sum of the values of f, and remember f is evaluated at these x points from 0 to 2 pi, and what I'll do is I'll just multiply the function value by the difference between consecutive x points. So this is like a Riemann sum. Very simple integration idea, and for that let's write, maybe let's do it up here. So I'll just put dx equals x2 minus x1. So this is the distance between consecutive grid points in the x grid. And then this is an integral approximation of the integral of f over the interval from 0 to 2 pi. Okay, so we are summing up a lot of boxes like this, and as we saw there was something strange here with the lin space. So actually, let me do this in a bit different way. So we take x from 0 up to n minus 1. Sorry, now I'm completely confused. Let's put oh, why am I completely confused? So, okay, next minus 1. Yep. Yep. Tässä siis oikeastaan niin kuin, oikeastaan tässä on siis funktio f pisteessä xj. Oikeastaan näin pitäisi kirjoittaa, joo. Kyllä, mutta tavallaan siis tuossa Matlab-notaatiossa oikeastaan niin tämän vektorin j's alkio on niin kuin määritelty näin. Tämänkin mä oon tehnyt niin miljoona kertaa. Miksi mä nyt sekoisin näin pahasti? Mutta eikö tämä nyt mene oikein? Mun mielestä tämä menee nyt oikein. Okay, and then we have here, and actually we can take this out because this is a constant. We can take it out from the sum. So I think this should be now the average of f. Let's see what happens. Let's plot let's do a new plot. Figure 2. Let's plot first the function f, and then let's put hold on, and let's plot our best possible approximation of f. So actually, let's plot x and a0 times ones of size x. Let's plot that with blue, for example. Blue line, and now I really hope that this works because we have 2 minutes left. So, well, we managed to finish the computation of the zeroth order Fourier approximation of f. So this is the best possible constant approximation to our red function. But everything gets much more interesting when we start adding more and more frequencies to the picture, but we will do that next week. Thank you. So okay, let's continue our study of Fourier series. And last time what we did was we defined our function at 2048 evaluation points. The evaluation points are defined like this. So they start from 0 and they go almost up to 2 pi, very close to 2 pi. Why almost up to them? It's because then we get our numerical integration right. And in the numerical integration, we need to compute areas of some boxes defined by our function, and the base of the box is always the difference between consecutive x grid points. So this dx is the length of the base of the rectangle whose area we are computing. And then we construct our f. First we take just a very simple rooftop function. First I define it as just identity, and then for x values larger than pi, I actually let it come down. What I mean by this, let me just run this so you'll see. So in red, you see our function defined from 0 to 2 pi, and the blue line is actually the constant approximation we computed last time, and the constant approximation was computed like this. It is the average of our function f computed as the integral of f. If in case you don't see why this is an approximation of the integral of f, please sit down and think about it for a while. This is just the sum of the areas of those rectangular boxes we discussed with the midpoint rule, and the integral is divided by the length of the interval. So this will give the average value of the function f. And that's why we see here in blue the average value. And next we start adding more Fourier series terms. So as you may recall, we are writing something like this. We are approximating f with a series like this, and now we'll start playing around with this n. So we start with n is 1 and then start adding more and more terms. What are these an and bn? They are computed like this. They are actually certain kind of inner products, but we can also just take these formulas here and just compute those values. So we have zeroth order Fourier approximation there, and then adding more terms. So let's choose n equals 1, and we need to compute a bunch of values, but let me first just compute, let's call it a1, just simply a1 like this. And what do we need to compute? Let's peek again here. So a1, when n is 1, we have just the cosine of x inside the integral, and of course times fx. And we divide by pi. This is the number we need to compute. So we have this 1 over pi times the integral. And the same way than before, the integral will be sum of the areas of the rectangles. The base of each rectangle is dx. And what is the height of the rectangle is the function value at the x points. And the function would be here f pointwise times cosine of x, right? And actually this dx inside the sum is useless because it's just a constant. We can take it here and remove one pair of parentheses. So this should be our A1, and then question, yes? F is good question. Why do I have a dot here? So let me make an example. Let's put temp1. Let me put this to be like 1, 2, 3, and temp2 equals 2, 2, 2. So we have two vectors. So temp1 is this, temp2 is this. And now if I want to multiply temp1 times temp2, what happens? Any ideas? No ideas? Let's test. No, we can't, because this is a matrix multiplication. If we want to multiply these two guys, we need to take care that the matrix dimensions are right. So the first is a vertical vector or horizontal vector, the second as well. So if we drop the second one to be a vertical vector, we can multiply, and we get the inner product between these two vectors. But this is not what I want when computing the integral, because in computing the integral, we want to multiply a function of x by another function of x. We want to multiply these function values at each x point. So there, what I actually want to do is do temp1 dot multiply temp2, which means pointwise multiplication. Remember, we had temp1, temp2, and then I multiply. So you see what happens. We multiply 1 times 2 equals 2, 2 times 2 equals 4, 3 times 2 equals 6. This is the pointwise multiplication, and that's what we want in our numerical integration here. So in this vector we have values of the function f at the x points. Here we have values of cosine at the x points, and we make pointwise multiplication. So then we have this A1 computed, and actually now we can try another figure to see what's going on. So actually now we plot again. Let's make figure number 3. So here we plot f, and then we plot our approximation, which actually I think I will now write here. Our approximation equals the constant term plus, now we have something more. We have A1 times cosine of x. our approximation is a little bit better than before, hopefully better. Let's see. So we plot x and the approximation in blue, and let's see what happens with this. So in this approximation, we have two terms. We have the best possible constant, and then we have just the right amount of cosine, so that the result is trying to go as close to the red function as possible. So it's already kind of a good job here. At least it looks already a bit like our function. Let's then add our sine term and just think a little bit while I write, how will this picture change when we add the term containing sine x? So what we need to do now with sine x is that we need to compute b1, which is the same thing than this one, except for having sine. And in our approximation, we put b1 times sine x. Okay. Any guesses? How does our picture change? Come on, one of you must have a guess. You can guess. This is a guess. Okay, Keith.
On the line, you will have more
Oscillations? Okay. Okay, one guess is given. More oscillations in the line. Any other guesses? How will it change? Okay, I don't torture you anymore. Let's see what happens. Now, as you can see, we get pretty much exactly the same picture. Is this really true? We can check what is the value of our b1. You see, b1 is practically 0. In computational mathematics, 10 to the minus 17 means 0. That's the machine epsilon. I mean, this is smaller than the accuracy of floating point numbers. So this means that the portion of sine x in our function is 0. There is nothing to the direction of sine x in our signal. And maybe why would that be is that our signal looks like this. It looks more like a cosine than a sine somehow. So there are really, I mean, the inner product between, I mean, how to explain this one? The sine, you know, the sine starts from 0, it goes up and back to 0 at pi, exactly where the peak of our function is. And then the sine does exactly similar negative loop on the other side from pi to 2 pi. And our function is just identical, of course reflected but identical. So these two pieces of the integral perfectly cancel each other. So there is nothing to the direction of sine x in our signal. But anyway, so this is like adding one more term, or let's say two more. And then let's compute with arbitrary n. Okay, the n actually, we didn't use the n here at all. So let's take n here to be, let's say, 2. And let's put here A vec and B vec. So let's compute the vectors. So these are actually, let me just initialize these vectors by zeros. So let's say we have one row and n columns in both cases. And next we need to fill in these A and B coefficients. So we make a for loop for I equals from 1 to n. And inside this for loop, I want to fill in both A vector and B vector one by one. The computation is pretty much already here. I just take these, I put them here. So A vector I equals that one. And let me, oh, actually, let's change this to, I'll be brave and just use n. Although it feels not right somehow, but I'll just do it. So we go from 1 to capital N and fill in the values. And now something is missing here. What is missing? Yes. Cosine nx and sine nx. Thank you. Exactly. So let's run this. And we'll see we have A vector and B vector. Well, the sine terms seem to be practically zero all the time, but also the second cosine seems to be zero. And then, well, let's compute even a couple more and see how they look like. This A vector. So you see, I'm making a conjecture here. You see, every other one of these is zero, and every other one contains some information. And the B vector, that's just zero all the time. That there is no sine-like behavior in our example function at all. Okay, but then we need to compute the approximation. So previously we did the approximation in this way, but now we need to do a for loop. So we could, for example, start by using the zeroth order constant approximation, and then we need a for loop to fill in our information we just computed. So now this approximation equals approximation plus a new term. Here we take this A vector A of n and we multiply n times x. And maybe I'll just do a second line for the other guy. So here, and we have from B vector n times sine. Although for this particular signal, these will always be practically zeros. But we will use another function very soon. So then actually these are important. Okay, and then let's make a picture. Fourth picture, and we'll see what happens. So this is the previous one with just one cosine term, constant plus cosine term, and here we have now cosine x, cosine 2x, cosine 3x, and cosine 4x terms. And of course the sine ones as well, but the coefficients are zero, so it doesn't matter. So you see our approximation is getting better. And of course we can now, since we have this general approach, we can put here more terms. So now you see our approximation is getting better and better. It's doing pretty much perfect job elsewhere than here in the corner. That's kind of supposed to be difficult because, you know, we have this pointy function with this non-differentiable behavior, and we are approximating it with a finite number of infinitely smooth functions. So obviously we cannot perfectly reproduce such a pointy part, but it's getting better, as you see. With every time we add more terms, it gives a better approximation. Next, we could change our function a little bit. For example, if we make another index, for example, x is smaller than 1, for example, and I will put f there in those points to 0, for example. Let's see what happens. So first I'll run that part. So our function looks a bit strange, but well, it's a function anyway. But it has a discontinuity now. Then we can make the best possible constant. Maybe not very surprising what happens here. And now when we have the cosine x and sine x terms, it's trying to approximate this function, which of course is impossible, but it's trying the best it can with only 3 terms. And now actually I think we have both a1 and b1 non-zero this time. For such a signal, the series needs also the sine part to make the best possible approximation. And then again, if we start with, let's say, 4 terms, the approximation is trying the best it can. And of course, again, we can take more points. It's trying, you know, you gotta give it a break. It's trying. It's only got 81 terms, but it's, I mean, yeah, it's doing what it can. And of course, since we are now computing, we can have more terms, no problem. And here you see the famous Gibbs effect. This is a property of Fourier series. Whenever there is a discontinuity and we are trying to express the discontinuity with a finite linear combination of infinitely smooth functions, something like this happens. This is the Gibbs effect. It is possible to work around this a little bit by suitably suppressing the high frequency coefficients, but maybe we can do something like that as well at some point. But anyway, that's the Gibbs effect. Now you have seen it, you know what Gibbs effect looks like. Any questions at this point? Yep.
Before we talk about the function having to be periodic.
Yes.
But this function is not periodic.
Haha, good question. Why would this be a periodic function? This is a periodic function. It has the value 0 at the starting point and also at the end point. So it is periodic, but this is a very good point, I think, because even okay, so we could also do something like, so index 3 when x is larger than 3, for example, and put here the value to be like 2. So this should look pretty weird already. We have a lot of Gibbs effect, and now I think the value at 0 is 0 and the value at 2 pi is 2. So this is not a periodic continuous function. This is a periodic discontinuous function. This function has a discontinuity at the point 0. And the point 0 is equal to 0.2 pi in the context of periodic functions. So it doesn't matter if there's a discontinuity, then there is a discontinuity. It can be anywhere, including the point 0. But it's not continuous. I mean, if we require a continuous periodic function, then the value at 0 and at 2 pi have to be the same.
Can you widen the range from 0 to 2 pi infinitely large period?
If you, I mean, with a very easy trick, you can use any finite period, so from any a to b, the interval. It's just a matter of scaling and translation. But if you go to an infinite period, then that would be more in the realm of the Fourier transform instead of Fourier series. The Fourier transform is defined for functions that are defined on the whole real line from minus infinity to infinity. And then it's a little bit different business how to calculate there, and that's not periodic then at all. That's just for any functions from minus infinity to infinity, although then the functions have to be integrable, so they have to go to 0 somehow near minus infinity and plus infinity. But that's a bit different game. We don't go into that in this course because we want to keep everything finite, including the range of definition of functions. But yes, there is a highly interesting world in that direction of the Fourier transform. Okay, so now next let's move on and try these methods for an actual signal. Or maybe, yeah, let's go to. Maybe I want to make a little more visualization for you actually with this approach. Just with this one, let's go back to 1 and let me modify this picture just a little bit. Let's have 2 pictures on top of each other. So let's put this to be the first of 2 plots, and in the second one, let's just take a look how oscillatory are the building blocks in our, how the most oscillatory element we are using in our series. So in the second plot, let's just plot the cosine n times x and sine maybe with black values, and here hold on. So here we have the approximation with, and let's also record the value of n here as a title. N equals, and then like this, so we can see, and then the font size. So here is our approximation with n equals 1. Here n equals 2, 3, 4, you see we are getting more and more oscillations in our most oscillatory building block for our function. And if we do this 40, you see we are using more and more oscillatory functions in our series. And all of them are involved here up to this. This is the highest frequency, but we have everything from constant, from sine x and cosine x, up to this is the maximum frequency. And what I did with the music in the beginning of the lecture, I was modifying the intermediate frequencies, putting them higher or lower. And that's something we will try next for a real signal, with a real audio signal. But I will stop this recording now and we'll make that one another video.